Hello everyone, I am Rajiv Kumar. I am a PhD student from the Indian Institute of Technology, Bombay. Today I will be presenting our work, Learning Unsupervised Cross-Domain Image-to-Image Translation using a Shared Discriminator. This work is co-authored by Rishabh Dabral and my principal advisor, Professor G. Sivakumar. In this presentation, I'll give a brief introduction to our work and other related works, and then discuss our proposed method. Then I will discuss about our results, Ablation Study, and conclude the presentation with a few closing remarks. First, let me introduce the problem of image-to-image translation. Image-to-image translation is a class of vision and graphics problems where the goal is to learn the mapping between an input and output image from a given set of input images and output images. It can be applied to a wide range of applications, such as translating edges to objects like shoes, handbags, etc. Similarly, for semantic image synthesis, or for translating labels to street scenes or faces, for translating aerial images to map, translating black and white images to color images, for translating daylight images to night images, for translating paintings to photos, and object transfiguration, etc. Our work is primarily focused on object transfiguration. While most image-to-image translation tasks involve translation over the complete image, there are cases where only an object of interest needs to be translated in the source and target domain. Let's consider the case of translating images of apples to oranges or horses to zebras. In both cases, only the object of interest needs to be translated without affecting the rest of the image or its background. This is called object transfiguration. Most of the prior work has focused on tasks as discussed in the previous slide. Adversarial methods that involve GAN either share network weights or use mechanisms that involve a primal GAN and a dual GAN. Methods like pix-to-pix, pix-to-pix HD use conditional GANs with the help of source-target pairs to learn a mapping from source domain images to target domain images. However, works like cycle GAN, dual GAN, and disco GAN learn the mapping without using any unpaired images. CoGAN learns the joint distribution of multi-domain images by sharing weights of generators and discriminators. Similarly, UNIT and MUNIT uses a shared latent space to learn a joint distribution of different domain images and achieves high-quality image translation. Many of the existing object transfiguration techniques assume the availability of source-target image pairs and expect rough alignment between them. Some of these methods need additional data as object mask or networks as pre-trained models. Mostly, the results of object transfiguration are prone to unwanted translation and image tints. Sometimes the object transfiguration is also incomplete. We focus on the above shortcomings on transfiguration techniques by proposing a framework that unifies the capabilities of multiple discriminators into a shared one to translate objects of interest while keeping their other objects and the background same. We propose to provide adversarial supervision using a novel shared discriminator common to both the generators without using extra networks, object masks, or additional data. Our goal is to learn two mapping functions modeled by two generators to translate an input image from one domain or the source to the other domain or the target and vice versa, such that the generated image follows the distribution of the target domain. For guided image generation, we use conditional GANs. Generator GAB models the mapping function from source domain A to target domain B, while generator GBA models the mapping function from source domain B to target domain A. An image pool is generally used to store a history of generated images to feed the discriminator in order to reduce the model oscillation during adversarial training. In our method, we associate an image pool to the generator of each task such that the translated images can be reused as inputs to either of the generators by pushing to one image pool or the other. We use this simple tweak to improve the robustness of the generators to deal with a variety of input images. Image pool IAB is associated with the task from A to B and therefore with the generator GAB, while the image pool BA is associated with the translation task from B to A and therefore with the generator GBA. Further details of the training stage and image pools will be explained in the coming slides. In our implementation, we use two training stages. The stage 1, where the translated images are pushed to the image pool of the same task, and the stage 2, where the translated images are pushed to the image pool of inverse translation task. Throughout the training process, the inputs to the generators GAB and GBA are A' from the image pool IAB and B' from image pool IBA. The image pools are initialized by the images of the source domain A and B when training begins. In training stage 1, in the initial stages of training, the translated images appear closer in appearance to the source domain with very few target domain features. Therefore, we interleave the translated images from the generator with the source domain images using the same image pool. Image pool IAB would pull in images A from the source domain A and the generated images B star from generator GAB, while IBA would pull in images B from source domain B and generated images A star from generator GBA. In the training stage 2, as training proceeds, the generators improve upon their translation capabilities and the generated images possess more target domain features and very few source domain features. Therefore, each generator can take the outputs of the other generator as adversarial images in addition to the respective source domain images. Image pool IAB would pull in images A from source domain A and the generated images A star from generator GBA, while image pool IBA would pull in images B from source domain B and generated images B star from generator GAB. Here we discuss the objective function of shared discriminator. All translated images are conditioned on the input images when subjected to the discriminator. The goal of shared discriminator is to classify the generated images into either belonging to domain A or domain B depending upon the source domain of the task. We avoid the usage of the terms real images and fake images and use abstract binary labels true and false instead. We assign true labels for domain B images and false label for domain A images. We exploit the fact that the data distributions of the source and the target domains of one translation task are the same as that of the target and the source domains of its inverse translation task. We assign the same labels for a domain irrespective of the task or their role in the translation task. In addition, we subject the shared discriminator to random domain B images labeled as true and domain A images labeled as false. These random images are conditioned on input images A prime or B prime depending on the translation task. The first three parts of the above equation are conditioned on input images A prime from image pool IAB and represent the translation A to B, while the latter parts are conditioned on the input images B prime from image pool IBA and represent the translation from B to A. The adversarial goal of each generator is to fool the shared discriminator into identifying generated images as belonging to target domain images. We enforce a pixel reconstruction loss between the generator's input and its output involving only one image translation. We choose a loss function that can preserve the median values so that the objects of interest are translated without translating other objects in the image or the background. This motivates the use of L1 pixel reconstruction loss between the input and output of each generator with additional help from adversarial training. We consider kernel inception distance and freshet inception distance as performance metric for our experiments. For both the metrics, lower scores imply better performance. And all experiments are either performed on apples and oranges dataset or the horse and zebras dataset. We refer to attention GAN paper for compiling the qualitative and quantitative results. The implementation is done using UNet and ResNet architecture. In table 1, we compare the FID scores of our method to other related methods on the horse to zebra translation task. We have better results than all methods except attention GAN, which is due to the use of attention mechanisms. In table 2, the FID scores on comparison of different network architectures are given. We observe that using ResNet architecture results in better scores than using UNet architecture. However, this may seem contrary for the apples to oranges task, but the performance difference is negligible. In table 3, we compare the KID scores from related works to our method. For zebra to horses and apples to oranges task, we could achieve the state-of-the-art results. In the other two cases, our results are slightly behind attention GAN method. Here we can see the qualitative results on oranges to apples task. The leftmost column is the input and the columns to the right show the translation results of other method compared to our method in the last column. We can observe that our results are quite close or sometimes better than other techniques. Also, our results are unaffected by unwanted translation of the background for this task. Here we can see the qualitative results on apples to orange task. We can observe that our results are quite close with that of many attention-based techniques. Also, most of our results are unaffected by unwanted translation of the background objects for this task. Here we can see the qualitative results on zebras to horse task. We can observe that our results are at par to many attention-based techniques, though some of our results trail to this attention GAN. There are no unwanted image tints. We can clearly see that the text is untouched in our method and the background is unaffected. Here we can see the qualitative results on horse to zebra task. We can observe that our results are at par with many attention-based techniques, though some of our results happen to have unintended background translations. There are no strong image tints or incomplete translations. We have performed various ablation experiments to highlight the contribution of various components towards the final performance. We perform an ablation study to isolate the effects and understand the effectiveness of various components of our method using FID and KID metric. We consider the original shared discriminator setup to be the baseline for comparing the variants 1 through 4. We modify the objective of the shared discriminator in a variant to see if all 6 components are really necessary. Out of the 6 components of the shared discriminator objective, 4 of them involves random source or target domain images, conditioned on either A' or B'. Since it may seem to be redundant, we deal with each domain only once and as target domain in this first variant. The source domain images conditioned on the input images are not subjected to the shared discriminator and avoided in the objective for this variant. The variant 2, we do not use the image pool. That is, the translated images or the outputs of generator are not reused. In the variant 3, we use the image pool without the training stage 1. That is, the translated images are reused by pushing to the image pool of the reverse translation task, but not to the image pool of the same task. In the variant 4, we use the image pool without training stage 2. In other words, the translated images are reused by pushing to the image pool of the same task and not to the image pool of reverse translation task. All the metric scores have been compiled on the horse to zebra task, as it is a tougher task than the apples and oranges task. Table 4 and Table 5 shows the results of FID and KID comparison trained on 128 cross 128 size train images and tested on 256 cross 256 size test images. Table 6 and Table 7 are results of FID and KID comparison, both trained and tested on 256 cross 256 size test images. In Table 4 and 5, the scores don't drop drastically when the discriminator components are removed while keeping image pools and both training stages. This implies that using image pools improve the robustness of the generator when the training image sizes are smaller than the test size images. However, in Table 6 and 7, there is no performance gain when the training images and testing images are of the same size. From Tables 4 through 7, irrespective of the image size used for training, the performance of the shared discriminator drops on removing the components of the objectives, which is pronounced in Table 6 and 7. It is obvious that in all the cases the performance drop on dropping each element, and the baseline consistently has the highest metric scores. Also, in all the cases, using the image pool with either of the training stages leads to the drop in performance. However, the scores don't drop severely for the variant with only training stage 1 compared to the variant with only training stage 2. I conclude the presentation with a few closing remarks. By introducing a novel shared discriminator setup, we improved the efficacy of the GAN used for unsupervised cross-domain image-to-image translation tasks. Also, we empirically demonstrated the effectiveness of our method on image transfiguration tasks and reported the qualitative and quantitative results on two datasets. Also, an ablation study was conducted to study the efficacy of the network's training objectives and architecture. Future work can focus on using attention mechanisms and patch-wise correspondence between the images. Thank you.